This conference will now be recorded.
Hello. Good afternoon, all. Welcome to the last session of the Faculty Development Program. Let me introduce our speaker, N. Srinath. N. Srinath is working as an engineer in application support field at Handritsu India Private Limited. Srinath completed his graduation from Adishankara Institute of Engineering and Technology, Kaladi, Kerala. He is currently having more than 4 years of experience in field of telecommunication and have worked on various network topology based on Ethernet architecture and legacy networks such as SDH, SONET, and PDH. Now, on behalf of Government Model Engineering College, Kochi, let me invite N. Srinath to deliver his lecture on Introduction to Optical Modules and Measurement Techniques. Over to you, sir.
Thank you so much. Thank you so much, Model Engineering College, for giving us this wonderful opportunity. And I hope everyone can see my screen and my audio is audible as well, right?
Yes, sir. Your audio is audible and the screen is visible. You can continue your presentation.
Okay, that's cool. So, starting off with today's presentation, I'll be briefly talking about optical modules. What are the famous optical modules that we technically use in an optical communication or an optical transmission, and what are the measurement techniques so as to ensure that the transmission is as per our standards or as per our requirements, right? So, starting off. Giving you a brief introduction about our Andritsu Corporation. So Andritsu Corporation is celebrating its 125th anniversary this year, and we are having approximately 4,000 employees worldwide with 23 sales offices and 8 different manufacturing and R&D units worldwide, right? With telecommunication test and measurement business as our core business, Andritsu is also engaged in various other businesses, which includes inspection equipments for food products, information and communication equipment and devices. So apart from being a pioneer in test and measurement business, we are also actively involved in various other businesses as well, thus making us a global market leader. We do have our locations, basically starting off with in Japan. We do have our research and development in Atsugi Kanagawa, whereas we do have our development and manufacturing unit in Fukushima, right? So in India, we are actively based out of 3 different locations. One in the north, we are based out of Noida, whereas in central part of India, we are based out of Hyderabad, and down south, our head office is in Bangalore, right? So now let's start off with today's topic. Before we move on to the testing part, let me just give you a brief idea about the current market scenario, right? So taking into consideration the current prospects of in optical fiber communication in India, before we move on to optical fiber, right, let's start off with the traditional the copper cables that we used to have earlier. But surprisingly, in India, it still has a market penetration of approximately 86.9%, right? I'll just use a pen. Okay, sorry. We do have a market penetration of approximately 86% still now for the conventional copper cables, and has only up to 2 Mbps of transmission speed. And it's sort of an obsolete technology, as it cannot carry that much of data, as it is pretty much evident, just of 2 Mbps, which is definitely not as per the current standards that we do have, since 5G and everything is just being deployed throughout the country, so throughout the world. So 2 Mbps is definitely not as per the standards. So this particular 86.9% is being largely handled by MTNL and BSNL, right? And private telcos has less than 10% of that particular establishments. Moving on to the next part, we do have the coaxial or the cable modem lines, which has approximately 6.23% of market penetration and has a data rate of up to 3 Mbps. Since these coaxial cables does require a significant amount of investment so as to increase the data rate capacity or the data rate capacity, right? Thus it has a a disadvantage in that prospect, whereas currently majority of the cable operators are using this mode of communication. Moving on to the next part, we do have the wireless technology, where we do have market penetration of approximately 2.15 percentage and a speed of 2 Mbps, which is the 3G speed, to be more precise. Since there is a severe spectrum crunch for this particular wireless to showcase its full capabilities, thus it inhibits its capacity, right? And the majority of the mobile operators, the private mobile operators such as Airtel, Tata Tele, are using this particular mode of communication. Moving on to the one of the future of telecommunication, or would be the optical fibers, which only has 0.24 percentage of market penetration, has significant speed, when we compare it to the conventional or the other modes of communication. The main problem is it has a high one-time cost. As you can see, it has a high one-time cost, but at the same time it also ensures that the high data rates are being achieved. And majority of the telecom providers such as Tulip and few cable operators such as in the metro regions have started deploying optical fibers as well. For example, Geo as well. So Geo fiber is almost in the deployment stages. So Geo being one of the the market telecom providers. So that is a sort of a brief idea about the market right now. And moving on to the market segmentation, how the market is actually segmented into different types on different categories. So first we do have what we call as a fiber or an SFP type. So SFP basically stands for soft form pluggable. So these are the units that is responsible for communication between point A and point B. These are the one of the most, you can categorize them as one of the most important categories or the units that is responsible for communication, optical fiber communication, right? So there are multiple types of SFPs. We do have SSF, which is the soft form factors, or the SFPs, which are basically having data rates below, or let's say up to 1 Gbps. And as we move towards CFP2 or CFP4, we are actually approaching data rates of up to 100 Gs, right? 100 GBE or 100 gigabit per second Ethernet, right? So these standards such as the SFP plus, which basically stands for 10 Gs, SFP28 is basically 25 Gs, and QSFP28 is 100 Gs. So these are basically different soft form pluggables which are actually having different data rate capabilities, and they have its own priorities, has its own importance in different market areas, right? Moving on to the next categorization point would be the data rate. So data rates, there are basically applications which only require less than 10 Gbps, as we know that the legacy networks such as SGH and SONET are come under this particular category, whereas as we move towards 100 Gs, we are more looking forward to technologies such as OTN and Ethernet, etc. Now, apart from that, we also have a category for wavelength, where such as 850 nanometer, and there is another band which is called as the 1300 band, 1300, right? So we do have a 1300 nanometer band. So these are basically the multi-longitudinal mode bands, whereas there are the 1310 nanometer and the 1550 nanometers are part of the single longitudinal. So I believe this currently I'm talking about market segmentation, right? So currently I'm talking about market segmentation, and 1550 and 1310 are basically for the single longitudinal modes. So I'll be talking in brief about in the coming slides, right? Whereas for distance, then we do have such as 1 kilometer, 2 to 10 kilometers, 11 kilometer to 100 kilometers. These are various distances that an optical fiber can actually travel. Then we do have more than 100 kilometers. So if you talk about the final limit that the optical fiber can take up to is actually around 125 to 130 kilometers. Beyond that, we need to have external equipment such as EDFAs, and also we need to have external equipments that needs to be introduced for traveling more than 150 kilometers or 200 kilometers, right? So I'll be talking about those in detail in the coming slides. Now, another next category would be the applications. So various applications are there, such as telecom, data centers, enterprises, where we are talking about access networks, right? The FTTH or FTTX, etc. So that comes under enterprises, right? So now, talking about the global optical transceiver market by the form factor. So you might be familiar how I was talking about different form factors, right? So you can see that this particular category of QSFP, that is from 25G, that is the from 40G, the QSFP 40G, and as we move towards QSFP 28, that is 100G. So this is going to take up the majority of the market in the coming coming stages with 5Gs and everything being coming into picture. So this is going to be taking the majority of the market share, whereas transceivers such as the SFP plus and SFP 28, which is on a lower data rate, such as the 10G or 25G, is not going to be that prominent because we are going towards high data rate requirements. So obviously this is not going to be that prominent. Whereas we do have other SFPs. So XFPs are way too conventional, because they used to be active during the early 2000s or probably before 2005, right? So CXFP, and these are all a pretty huge form factor SFPs. So these are going to be obsolete in anytime soon. So moving on to the testing part, let's start off with the optical modules and its testing part, right? So one of the prime component, to be more precise, in the optical communication is what we call as an optical emitter, and this is everywhere. We need to have emitters, right, for communication from point A to point B. So optical emitters basically work on a fundamental called as the ASE, or the amplified spontaneous emission. So what now the question comes is, what is this amplified spontaneous emission all about, right? So when there is an incident photon of h nu, I'll talk about what nu is. So when there is an incident photon of h nu, there is an electron in the non-excited state E1, which will thereby be excited to the which will thereby move to the excited state E2, and when it de-excites, it will release another photon, right? And the formula, or this is just an overview of what actually happens in an ASE, or an amplified spontaneous emission, right? And to put forward it in a theoretical way, it basically operates on the idea of electromagnetic energy, and can only appear in discrete amount as quantum, and these quanta are called as the photons. And these photons, when the energy is radiated, that is when the electron is electron comes back to the non-excited state E1, right? And this particular energy in one photon is dependent upon the frequency parameter, the nu. This is the frequency parameter. And typically optical emitters are being basically classified into two types: the LEDs, light emitting diodes, and the laser diodes, right? I'll be talking about the primary difference between LEDs and lasers, because there is a high tendency that you might actually confuse between LEDs and lasers when we talk about optical transmission, right? Moving on to the next part. So remember, I was talking about different wavelengths, right? 850 nanometer, 1300 nanometer. There I mentioned two terms: single longitudinal mode and multi-longitudinal mode. So we'll talk about what these SLM and MLM is all about. Single longitudinal mode basically has one mode. You can see one particular mode over here, whereas MLMs have multiple modes. And there are different applications or different modules that come under a single longitudinal mode and multi-longitudinal mode, such as the DFB, ECL, TLS. I'll be discussing in brief what these are all about, right? And in MLMs we do have VC, SEL, and FPLD, etc., right? So optical transmitter types, as I was talking about, we do have DFBLD, which is called as the distributed feedback laser, right, which comes under the SLMs. We do have ECL, the external cavity laser. We do have TLS, the tunable laser source. So these are all coming under the what we call as a single longitudinal mode, whereas we do have VSCEL, which is called as a vertical cavity surface emitting laser. So one of the most common, or one of the most famous example for a VSCL is face scanning. So we do have face unlock in our phones, right? Initially we used to have these VCSEL for these face unlock and all things, because they are so called the vertical cavity surface emitting lasers, right? Then we do have the FPLDs, the Fabry Parrot laser diode, and the LED, the light emitting diode. So these are all part of the what we call as the multi-longitudinal mode. So what now coming on to the basic classification, or what is the primary differentiation between the common LED and a laser diode is, laser diodes generates coherent and intense light of very narrow bandwidth. We have to have emphasize on this particular term, very narrow bandwidth. What is the line width of about 2 nanometers compared to that of a 50 nanometer. So 50 nanometer is a pretty huge line width when we compare to that of a laser diode, right? So LEDs, or common LEDs, have a line width of approximately 50 nanometers, where we do have a line width of approximately 2 nanometers. So remember, I was talking about multi-longitudinal mode and single longitudinal mode, right? So the line width of that single longitudinal mode is typically around 2 nanometers, whereas for a conventional LED or the MLMs is approximately 50 nanometers, right? And laser diodes are constructed much like LEDs, but operate at a higher current levels. So since we are talking about narrow bandwidths, thus they have a higher current levels, right? So moving on to the just giving you a brief idea about what the FP and DFB is all about. So the Fabry Parrot laser is mainly used for low data rate or short distance transmission. So low data rate and short. So we have to so one thing that we get to know from this particular sentence over here is Fabry Parrot will be involved in MLMs. So that is pretty obvious, MLMs. Now what are the wavelengths? That will be 850 and 1300 nanometers, because those are the wavelengths that are actually being used for short distance transmission, right? Whereas for DFB or the distributed feedback lasers, they will be deployed for high data rate or long distance transmission, which are generally above 40 kilometers. So one thing that we get to know from here is the MLMs are basically deployed for short distances, whereas the DFB or the single longitudinal modes are basically deployed for larger or the longer distances, way above 40 kilometers, right? And the wavelengths that are actually in this particular DFB, where this DFB functions is 1310 nanometer and 1550 nanometers, right? So moving on to the just looking at the spectral characteristics of the FP and the DFB laser, right? So Fabry Parrot, as mentioned earlier, comes under multi-longitudinal mode, whereas a DFB laser comes under a single longitudinal mode. So a spectral width of a DFB laser is generally narrow, as mentioned earlier, which is a single longitudinal mode, whereas a Fabry Parrot laser has a relatively wide spectral width and is coming under multi-longitudinal mode. So as explained earlier, the line width or the spectral width of a DFB laser is very narrow, because as you can see from this very spectral analysis as well, this is just the spectral width of a DFB, whereas the spectral width is this much in case of a Fabry Parrot, right? So coming on to the next component or next important aspect or a next of optical transmission is the LED. So LEDs basically has a p-n junction kind of an architecture, where the light is generated and passed through the optical lenses. So rather than generating heat at the depletion region, we are seeing light being generated over here, and they typically work in two regions, namely the visible spectrum and the IR region, right? So that's where the LEDs fall into, right? So moving on further, another primary or the most one of the most used component is the modulator. So we know that modulation is one of a prime aspect when we talk about transmission, right? Any transmission, take into consideration any RF or optical or any transmission, we need to have modulations, right? So in case of optical transmission, we do have technically two different types of modulation. One we call it as a direct modulation, and another we call it as an external modulation. Direct modulation is when we have a modulated electrical signal directly being implied onto a laser diode, whereas in case of an indirect or an external modulation, we do have something called as an external modulator in picture, right? And a laser diode will send its continuous wave or the information, right? And it will be modulated with an electrical signal, and a modulated signal will be coming out at the output, right? So as we are talking about, so this is how an SFP, remember I was talking about the SFPs, right? So this is how the SFP looks like actually. So this is the form factor of the SFP, right? So technically in an SFP there are two prime components. One is called as a TOSA and one is called a ROSA. ROSA basically stands for receiver optical subassembly, whereas TOSA stands for transmitter optical subassembly, right? So the TOSAs will be responsible for transmitting the signal over an optical fiber. So it's like we do have point A and we do have point B, right? There will be an SFP over here. There will be SFP over here. So the TOSA will be responsible for transmitting the signal over the optical fiber, which will be received by the ROSA at point B, whereas the TOSA of point B will be transmitting a signal which will be received by the ROSA of point A, right? So that's how a point-to-point communication actually happens inside an optical fiber or an optical transmission system, right? Now we need to analyze, we need to analyze what is actually, so apart from having a basic idea about all the optical components in an architecture, right, we need to ensure that they are working as per the standards, right? So technically there are three as of three famous organizations that actually lay down different standards, one being the ITU or the International Telecommunication Union. Then we do have the IETF, which is the Internet Engineering Task Force. We do have IEEE, which is the Institute of Electrical and Electronic Engineering. So these are the three different organizations that is responsible for laying down different standards in case of an optical fiber communication. So using an optical spectrum analyzer, we can ensure that whether the components of an optical transmission system are abiding to these standards, right? So Anritsu's MS9740B, which is our optical spectrum analyzer, has a wavelength range of 600 to 1750 nanometers. The reason being we are incorporating such a wide range of wavelength is because, as explained earlier, MLMs and SLM, the multi-longitudinal mode and the single longitudinal mode testing has to be conducted. If we are talking about applications where we are having wavelengths such as 850 nanometer or 1300 nanometers, which is the short distance wavelengths, we need to have testing for that as well. Whereas for single longitudinal mode or 1310 nanometer or 1550 nanometer, we need to conduct testing for that as well. So having a wide wavelength range is of utmost importance when we take into consideration an optical spectrum analyzer, right? So as it's quite evident from the wavelength range, it supports both single mode and multi-mode fibers, has a wide dynamic range of up to 70 dBs, and has a sweep speed measurement of just 0.35 seconds for a span of 30 nanometers. So you can see the sweep speed, superior sweep speed, when we take into consideration such a huge wide wavelength range, right? And talking about the application, there are different application menus. I'll be talking about brief in those what are those application menu is all about. So there are 9 different application menus in an optical spectrum analyzer, depending upon different DUTs or device under test that we do have, such as the LEDs that I was talking about. So some people might have to test LEDs, some people might have to test FPLD. So we need to have different applications inbuilt onto an optical spectrum analyzer so that testing can be conducted successfully. Now, what are these 9 different applications that we are talking about? So starting off with the LD module. So we have, I talked about TOSA and ROSA, right? So evaluation of the optical transceiver is very important. That is TOSA ROSA testing. We do have the DFBLD, as I have explained, a single vertical mode spectrum. We have the FPLD, which is multiple discrete wavelength spectrum, that is multi-longitudinal mode. We do have the conventional LEDs, a wideband light source spectrum. We do have PMD. So PMD is PMD basically stands for polarization mode dispersion. So there are various non-linear and linear factors that are in an optical fiber that actually affects the transmission from point A to point B, such as dispersion or attenuation. So we need to ensure that PMD is also tested in an optical fiber so as to ensure the communication is proper, right? We do have optical amplifiers. So I'll be talking a bit in detail what these are, because this is a pretty important component when we take into consideration an optical transmission. We do have the WDMs, or wavelength division multiplexing. So these WDM and WDM filters are being deployed basically to cater to very high data rate requirements, right? So these are the different 9 applications that the optical spectrum analyzer actually takes care, analyzes when we take into consideration an optical fiber communication, right? So optical spectrum analyzers, this is how an optical spectrum analyzer window looks like. So right, so we do have so all the applications that you actually select, I remember I was talking about 9 different applications, right? So each and every application that you select will be popped up over here, the DFBLD, and the parameters associated to that DFBLD will be popping up over here in this column over here, such as we do have a peak. So every a single longitudinal mode has a peak, right? A peak. So a peak will be displayed over here. Then we do have a second peak. So second peak is basically a side mode peak, as you can say, to be more precise, right? Then we do have this sigma, or the standard deviation, right? So there are different parameters such as the SMSR, side mode suppression ratio. So these are different parameters that we need to take into consideration so as to ensure that the module which is under test is abiding to the standards, right? So this is our typical measurement example of a DFBLD looks like, right? As I mentioned earlier, it's a single long, it works under a single longitudinal, it comes under single longitudinal mode, as you can see a single peak in the spectrum analyzer, right? So talking about evaluation of the optical transceiver, a pretty big figure, I'll just break down into different sections, right? So an SFP, which I have explained earlier, as you can see, this is the SFP which is under test, right? So we do have an amplified spontaneous emission. It's sort of a unit which is basically, let's say it's basically a input, or let's say it's basically a light source. Let's break it down into a simpler terms. It's a typical light source. It will be given to an optical attenuator, which will thereby work as an input for the optical transceiver. The output of the optical transceiver will be given to the optical spectrum analyzer for analysis, whereas this particular unit, I'll be talking about what these instruments are capable of. Just to give you an idea, these basically have 2 different inputs. So depending upon your requirement, if you're working on an optical input, you can actually have an optical SFP being plugged into this particular instrument. If you're working on an electrical input, you can just remove that electrical and it will just work on an electrical input, right? So an optical attenuator over here, there's another optical attenuator, so as to ensure that the the input is well within the standards, or well within the threshold value, right? It will be given to this particular instrument, or you can actually give an electrical. So it's basically an or over here. You can either give it an optical input or an electrical input, and depending upon that, it will give you a data. I will be explaining about what this particular diagram is, or what this thing is in the coming slide. It will give you an information, and depending upon that information, you can actually judge whether the transmission is happening as per our standards or not. So optical transceiver analysis will be done by the spectrum analyzer, whereas the transmission capabilities will be handled by these instruments, right? So I hope you might have got a bit of an idea. So typically this is so what this thing is called as, it's basically called as an oscilloscope or a bit error rate tester. So I will be talking about what these bit error rate testers and sampling oscilloscope is all about, right? So I hope you might have got a bit of an idea so of what how a testing of an or an evaluation of optical transceiver is done, right? So now, what are the, so this particular window is similar to that of the DFB-LD. The only primary difference is, as you can see, the application is changed over here to LD module test, right? And depending upon that, all the necessary parameters such as the central wavelength, the power, or mode offset, or SMSR, second peak, etc., or the noise level, signal to noise SNR value, or the OSNR value, optical signal to noise ratio. So all those values will be displayed, and this will give us an idea about what is the performance, or what is the whether it is abiding to the standards or not. So this will be about the optical spectrum and optical transceiver evaluation in an optical spectrum analyzer, right? As mentioned earlier, parameters such as central wavelength, optical level, OSNR, etc., are pretty important when we take into consideration the evaluation of an optical transceiver, right? So moving on to the next, remember I was talking about one of the applications, 9 applications, where I talked about optical amplifiers, right? So there are multiple optical amplifiers in an optical fiber communication, such as Raman amplifiers. So there are multiple others. One of those most commonly used is EDFA or an erbium doped fiber amplifiers, right? So erbium doped fiber amplifier is an optical amplifier used in the CAL band. So CL band is basically somewhere around the 1550 nanometer wavelength range. So that is where the CL band actually lies, right? Where the loss of the telecom optical fibers. So there are multiple losses. Remember, I was talking about multiple linear and non-linear losses in an optical fiber, right? So as to compensate for the loss, we need to have something called as an EDFA, right? It was invented way back in 1987, and now it is one of the most commonly used to compensate for the losses in an optical fiber for long distance communication. So say for example, if you want to if we want to transmit something from Kerala to Bangalore, or say something from Chennai to Kerala, so that is approximately 600 to 1000 kilometers, right? So that is the distance range, right? So for such a huge distance range, and remember I was talking in my previous slides that the maximum that it can go up to is 125 kilometers, right? The SFP is maximum that is developed is up somewhere around 125 to 150 kilometers. So what will happen, so what happens when there is an application where we need to transmit for more distances, right? So there we have something called as an EDFA, which will thereby amplify the signal. There are multiple amplifiers such as a booster amplifier or a BA. We do have different inline amplifiers and a pre-amplifier. So these will amplify the signal to a specified level so that the transmission can be successfully established, right? So that's the EDFA part. And so how the analysis is actually done. So we do have a LD module. We will give a direct input, and when we will have an EDFA being deployed. This is actually the device under test. Then we will see the output, right? So you can see P out waveform after amplification, it has been amplified to a specified level, whereas P output before amplification, right? So you can see there's an amplification that has happened, right? So there are multiple methods that you can actually use to see these amplifications, in an optical fiber, optical spectrum analyzer. Basically to calculate two different parameters, the gain and the noise figure. So these are the two important parameters and that we take into consideration of an optical EDFA analysis. These two, gain and the noise figure, right? So talking about WDM, so there are multiple multiple applications it's out there in the market right now, right? So there are Ethernets, there are OTN, SONET, SGH, etc. So there are multiple applications that is part of the optical fiber communication, right? So Ethernet will be deployed one particular wavelength. Okay, so there will be a one particular wavelength for Ethernet, there will be another wavelength for OTN, there will be another wavelength for SONET, and they will be spaced at a value of 100 gigahertz or 50 gigahertz spacing, right? And they will be transmitted over a fiber communication. They will be demultiplexed at the far end, and this particular analysis can be done over here. So as you can see, there are multiple wavelengths, so it is quite evident that each and every wavelength value should be displayed under the optical spectrum analyzer, right? So as you can see, there are multiple wavelengths. Say for example, 1552.340 was deployed for Ethernet, 1553.132 was deployed for some other application. So all those applications and the the spectrum analysis associated to that application will be displayed on the optical spectrum analyzer. And the Android OSA can support up to 300 channels. So that are the applications that it can actually support up to, right? Now, moving on to the next part. So remember, I was talking about this particular figure in that optical transceiver evaluation, right? So let's talk about what that figure was all about, right? We do have something called as a bit error rate test set in the transmission, optical fiber transmission. This basically ensures that the transmission of the optical fiber, or the transmission unit, or the DUT, is transmitting the data properly without any bit error rate. This bit error rate, right? We typically an ideal scenario is zero bit errors, but that's an ideal value, right? So what actually happens is we are actually generating ones and zeros per second, right? And we actually measure the bit errors after the passage from the DUT. How the error is actually being measured, that is via an module called as an error detector. This error detector. So the pulse pattern generator, the PPG, will generate bits in ones and zeros from this particular point. It will be given to a DUT, which will display this particular information, right? I'll talk about what this information is all about in the next slide, right? Then it will give out an information which will be given to ED, and it will do the comparison, right? So that's how the error detector actually functions, right? So now, what is this information all about? So this information is called as an eye pattern. As you can see, it resembles an eye, right? So this eye pattern is one of the methods for representing a high speed digital signal, as it's all digital, zeros and ones. So it is basically a method used for representing a high speed digital signals, right? So this particular eye pattern is an overlaid plots on a graph. It's basically an it represents the transitions, zeros and ones, of a single waveform. Say, see, as you can see, we do have a one over here. So it's an overlaid plot of these these transitions on a graph. So when we overlay these things onto this particular graph, you will see something called as an eye pattern, right? So what actually we do have over here is we do have an amplitude axis, we do have a time axis. So the time axis is responsible for calculation of phase margin, whereas the amplitude axis is responsible for calculation of the voltage margin, right? But this is not this actually does not give you, or this method should not be deployed for examination of protocols and data stream errors. So for this, we do have something called as a transport tester. So that is entirely different. This is just to ensure that the transmission is happening as per our standards or not, right? There are any bit error in the transmission network or not. So this is a tool which is basically used for detecting the causes of a degraded bit error or an amplitude and time axis, right? So that is a prime application of a bit error rate tester is all about, right? So let's observe the eye pattern in a detail, right? I mentioned about the voltage direction margin. So this information, this eye opening, so this is called as the eye opening, right? So this eye opening will give you the voltage direction margin, whereas this particular information on x-axis will give you a phase direction margin, right? And the eye pattern is dependent on two very important terms, the TR and TF. TR stands for rise time. So you can see there is a rise time over here, and TF. So there is a fall time over here. So this is the fall time, right? So we do have a TR and TF. So this particular opening is called as an eye opening, and the prime objective for achieving low bit error rate is to have a wide eye opening. So wider the eye opening is, ideal will be our signal, that is lower will be the bit error rate associated to the transmission. With larger the eye opening, receiver has the better ability to recognize zeros and one correctly. So larger the eye opening is, right, larger the eye opening is, the receiver will have the better understanding to segregate ones and zeros. So for example, if the eye opening is just like this, say, this is just the eye opening, so the transmit rise time and fall time is so closely packed that the receiver is not actually able to segregate what the ones and zeros is. So once the receiver has that sort of confusion, right, to segregate ones and zeros, we will start seeing bit error rates or BERs. So the primary objective to have a low bit error rate in the transmission network is to have wider eye opening, that is helping the receiver to judge what a 0 and what a 1 is all about, right? So typically the eye opening is actually calculated with a 10% rise from the initial, because this is an ideal scenario. We don't see such a such a peak. Usually it's a slanting, a gradual increase in the TR rise time and a gradual decrease on the fall time. So that is the prime reason why we are taking actually a 10% rise from here and a 10% gap. So this is the reason, because it's not a steep, it's typically, this is an ideal scenario. Usually it's not this steep actually. This is not the typical the practical scenario. Typically what we have is a gradual decrease in the rise time, or a gradual decrease in the gradual increase in the, sorry, gradual increase in the rise time or gradual decrease in the fall time, right? So and these rise times and fall times are actually expressed in what we call as UIs, UI or unit intervals, which is equal to 1 per bit rate, 1 per bit rate, right? So that is how the TR and TF measurements is actually conducted, right? Now these are few pulse patterns. These are the pulse patterns before the overlaying is done, right? So we do have different pulse pattern, and if you have a good pulse pattern, obviously the eye opening will be better. If we have a poor pulse pattern, you don't expect it to have a good eye opening. It will always have a poor eye opening, thereby it will have a higher bit error rate. This is sort of an acceptable eye opening, but typically this is what we actually aim for, a good pulse pattern. This is what we actually aim for, right? So ideal eye pattern from a good pulse pattern is somewhat like this, whereas if we have a poor pulse pattern, then it's going to be like this. So as you can see, when we compare these two, the eye opening is much better in this case, whereas the eye opening is much poorer in this case. So obviously the bit error rate will be much more in this one when we compare it to this one, right? So when we talk about PPG, right, pulse patterns, so what are these patterns all about? So these patterns are what we call as a PRBS patterns, or a pseudo random binary sequence. So these are all ones and zeros. So how it is actually generated? So it is generated, or it is actually decided on length derived from a formula 2 raised to n minus 1, 2 raised to n minus 1, and the most common values is these, right? So more the value of n, more will be the number of patterns, right? So for example, if the value of n is equal to 31, obviously the number of patterns will be more, and more the number of patterns, more will be the test time, right? So more the number of patterns, more will be the time taken by the PPG to generate those patterns, right? So higher the value of n, more will be the test time. So that's how it actually is, and these patterns or these values of n's are actually defined by the ITU standards, right? And these are being followed rigorously throughout the entire telecom industry, right? And these PRBS patterns are actually generated by shift register stages or XOR gates, XOR gates, and basically consists of ones and zeros. So the n number is of ones, whereas n minus 1 are the number of zeros, right? So for example, if value of n is equal to 7, so 7 will be the number of ones, and 7 minus 1, that is 6, will be the number of zeros, right? So that is how the PRBS or the pulse pattern generator generates ones and zeros, right? Now, how to evaluate or how to get the necessary information from an eye pattern, right? Say for example, if for a good output, right, for a ideal or a good transmission, we need to have a symmetrical cross points, right? A symmetry of the cross point, so this is what we call as a cross point. So the symmetry should be ensured throughout the entire eye pattern, right? Low waveform distortion, we need to ensure that the distortion, so you see a lot of distortions, right? Distortions should be low throughout the entire eye pattern, right? A fast TRTF, that is, there should be a fast rise time and a fast fall time. What it will give us, it will give us a better eye opening. What happens if there is a gradual TR rise time? So a gradual will be somewhat like this, a gradual will be somewhat like this. So this is not what we actually want. We need to have a better eye opening, right? So we need to have a fast TR and TF. A low noise in the voltage direction of the eye, so we need to have a low noises. So these are the noises that we are actually talking about, right? So we need to have low noises and low jitter over time jitter, that is peak to peak. So I will be talking about what these jitter and noises is all about in the coming slides, right? And how this actually affects these eye patterns, right? So moving on with one of another category, or one of the important aspect of a signal is we do typically have two different types of signal: a single-ended signal, that is single-ended signals. We do have single-ended signals, zeros and ones, zeros and ones. So in case of a single-ended signal, if there is a noise or a distortion, it will thereby generate an error on the output part. For example, now let's take into consideration differential signal. So we do have a data and a data bar. That is, if data is 1, we do have data bar that is 0, right? So if there is a noise, it will appear on both data and data bar, and it will cancel out each other, and we can have a noiseless transmission at the output. So that's the reason why we choose differential ended signals over a single ended signals, right? So you can see the difference, why differential ended. So in every bit array tested, you will see a data and a data bar. So you know the reason why we now have data and data bars, right? Now, error detector or the ED module needs to synchronize with the PPG, right? So PPG and the ED needs to be synchronized so that both of them can work in tandem, right? So how that synchronization? So one of the method for that synchronization is called as a PRBS method, right? So let's take into consideration an example. So let's take into consideration example of a 2 raised to n minus 7 minus 1, that is value of n is equal to 7, 2 raised to 7 minus 1. If we input a PPG, if we input a PRBS pattern of this particular formula, that is 2 raised to 7 minus 1, we will, it will pass through different delay registers, and we will have a comparator over here which will compare it with a reference pattern generator. And if both the values are same, or if both the values are somewhat same, that is the error count is low, the switch will always be at the B position. If the synchronization, that is a successful synchronization, whereas if the error count is high, that is a failure in the synchronization, the switch will switch to position A. That's how a synchronization basically. So this is one of the examples of a synchronization happens. There are multiple other synchronization methods such as a pattern synchronization or data synchronization, right? So PRBS is one of the examples of synchronization between PPG and ED, right? So what are the prime causes for bit error rates, right? Prime causes for a bit error rates are, we do have something called as an external noise. If there is a noise, then that will lead to a bit error rate. There is something called as an insertion loss, which basically comes at a higher frequency. We do have a jitter and wander, which are short-term variations in the digital signal. Then we do have impedance mismatching, right? I'll be talking indeed what these things are in detail in the coming slides, right? So external noise. So this is an original signal. When it is degraded with a noise via transmission channel, we need to have an equalizer, or so as to compensate for that loss, so that we can retrieve back the original signal. Now, when we see a eye pattern for the same, this is this is how it looks like. Remember, I was talking about a symmetrical eye opening, a fast rise time and fall time. So you can see these are unsymmetrical eye openings, very gradual rise time and fall time. As you can see how this has actually impacted the eye pattern. This is definitely not tolerable, because we cannot actually, so the receiver is actually not able to distinguish what a 0 is and what a 1 is over here. It's basically a very poor signal, right? So noises should be eliminated so as to ensure that the receiver can distinguish between zeros and ones correctly, right? So remember, I was talking about something called as an insertion loss. So this insertion loss comes at a higher frequency, and the reason basically is, let's take into consideration a coaxial cable where insertion loss basically comes into picture due to different environmental scenarios such as corrosion, or let's say in a slag in the cable, or improper connections. So these may lead to something called as an insertion loss, which basically pops it at higher frequencies. So even if the amplitude of the signal is the same, these are basically transmitted at different frequencies. So you can see how higher frequency signal has its amplitude shrinked. So amplitude of a higher signal was actually decreased, whereas the 1 gigahertz one was typically the same at the output, but whereas in case of a 5 gigahertz, you see how it actually shrinked. So higher insertion losses pops it at higher frequencies, and you can see how this thing has impacted the eye pattern, right?
Excuse
So
me,
moving
sir.
on to the next part. Yes, sir. Yes, sir.
Sorry to interrupt. We have to wind up the
Uh-huh.
session at 3 p.m.
Sure. I'll just quickly move ahead, right? Just
Okay, sir.
maximum 5 minutes, 5 to 7 minutes, right?
Okay.
Okay, thank you. So another important parameter is what we call as a jitter and wander. And so these jitter and wanders actually affect a stream. So you can see how a jitter has thereby missed few bits, right? Zeros and ones. So you see something is missing, right? So that has actually affected the transmission capabilities, right? There are different types of jitters such as RJ or random jitter, deterministic jitters, DJs, etc. So how this jitter has affected? This jitter has affected in this manner. This is actually how a jitter is actually calculated, peak to peak, the crossover point. This is how a jitter is actually calculated in the bit array test set, right? Now, impedance mismatch. We need to ensure that the transmission path is having a 50 ohm. The reason behind 50 ohm is it's basically a balance between low losses and maximum efficiency, right? So that's the reason why we have 50 ohm in the transmission path, right? And we need to ensure that the impedance is equivalent throughout the entire point A and point B, so that we have impedance matching. If there's an impedance mismatch, this will thereby lead to bit error rates. This is an overall scenario. We have having so when there is a miss, we have a bit error rate. Bit error, sorry, we do have a bit error over there. When there is a miss, zeros and ones, we have a bit error, right? This is how a calculation is basically done, right? Where are bit errors actually used? Where there are multiple areas such as telecommunications, AOCs, chips, server, data centers, core aggregation such as the metro network. So these are different places where a bit error rate test set is actually used. We do have different instruments such as the MP2100B, which basically is used for these particular applications. We do have the eye pattern over here. We do have the bit error rate measurements on the right hand sides, right? There are multiple applications such as the transceiver evaluation. We do have the active optical cable measurements. We do have BOB, or this is basically a combination of TOSA and ROSA, bidirectional optical subassembly on board. So for those evaluations, we are using these instruments. The prime difference between both the instrument, the MP2100B and 2110A, is the data rate. So for higher data rate, we use this instrument. The higher data, that is more than 14 Gs, right, per channel, right? So you do have multiple instruments such as CRU or a clock recovery unit. We do have datas and data bar, as I mentioned earlier. We do have a scope over here. We do have a bit error. So this scope is what we call as a sampling scope, whereas we do have a bit error rate over here, right? So Andritsu's has its solution throughout the entire application, starting from data rates of up to 400 Gs up to as low as 10 Gs. So you can see there are different instruments that we do have, right, for different optical modules, starting from the R&D stages to mass production stages. Summarizing the presentation, we do have Android SUSE solution throughout the entire architecture or the entire market scenario, starting from a simple, antennas and cable system, moving to a core or backhaul network itself. So for antenna system, backhaul, base station, or air interfaces, Android SUSE as you covered throughout. So that was about the presentation, and I hope it was informative. I hope you might have gained a little bit of idea about what the scenarios. I had to increase my speed a little bit towards the end so as to abide to the time period, right? So if you do have any questions, please do let me know. I'll just stop sharing my presentation over here, right? And please do let me know if you do have any questions.
Thank you, sir. Let's move on to the questionnaire session. If the participants have any doubts, you can directly ask to the speaker.
Yeah, please either use a chat or you can just unmute yourself and you may ask questions, please.
Sir, wait for 2 minutes.
No problem, no problem. Yeah, please. I hope I wasn't talking too fast, right? I hope you might have understood something about the network and all.
Sir, due to the time constraint, we can only wait sometime only because we have a online assessment at 3 p.m.
Okay, no problem, no problem. We can have. I'll believe we do have 1 more minute, so just let's wait for 1 more minute and see if we do have any
Okay, sir.
questions, and right, and we can wind it up. I hope this presentation was a little bit informative because I know that I moved a bit too fast towards the end part, but I hope you might have got an idea about what the transmission is all about. Thank you so much, Mukesh sir.
I hope the participants are waiting for the online test since
Okay,
they are
okay.
not responding.
No problem at all, no problem at all. So let's wind this session up. Thank you so much, Model Engineering College, for giving Android SUSE this opportunity to present, give a bit of information, right? And I hope it was informative, and I hope it helped all the listeners as well.
Okay, sir. I think it's time to wind up the session. I take this
Sure.
opportunity to thank Srinath. Thank you for your excellent presentation. We are
Thank you so
grateful
much.
for the time and effort you took to share your knowledge and experiences in the area of optical modules and measurement. We truly appreciate your willing to give your talent to enrich the knowledge of upcoming young minds. I would like to thank you on behalf of Government Model Engineering College, organizer, coordinators, and all the participants present here. I hope all enjoyed his presentation. Thank you, sir.
Thank you so much. Yeah. Take care, everyone. Bye-bye.
Bye, sir.
Dear participants, very good afternoon to all. I am Dr. Laila, the coordinator of this FTP is speaking now. So after the coming section on test or exam, we have a feedback section. So actually that feedback section is open to the participants, and I request the participants to give a feedback because we need that. Then only we can improve or correct our issues or problems what we have faced, and we can correct it when we organize in the next FTP. And this is the first time we are organizing an FTP in online, ACT Adult FTP. This is the first time we are organizing in online mode. So we expect a good response. Okay, thank you.
Now it's time for online assessment. It will be a 30 minutes MCQ examination. As I have already mentioned in the first day of the FTP, the e-certificate will be provided by ATAL Academy upon the successful completion of FTP containing 80% attendance and having acquired at least 60% marks in the online assessment. Now, let's move on to the test and feedback session.
Hello.
The question is provided either in the email or in the WhatsApp group. You can attend the
What is the
exam through
name
the
and
link
city
provided.
mentioned? Excuse me.
Question is already given through WhatsApp.
After the successful completion of the online assessment, all the participants are requested to rejoin the meeting for the feedback session.
This conference will now be recorded.
Thank you all. I hope all of them have attended the online assessment test very well. Now there is an important announcement requesting the participants to fill the feedback form in the ATAL website other than the feedback sent by the organizers. it is mandatory to fill the feedback form, complete assessment to get the e-certificate of the faculty development program. Now, let's move on to the feedback session. Participants can now free to give their valuable feedback and reviews on the FTP webinar. Participants willing to give feedback can give their names by posting them in the chat box so that I can read out your names one after the other. I welcome Anita Saracharian for the feedback.
Good evening, everyone. I'm Anita. First of all, I'd like to thank Laila Amos and her team for organizing a great event even at this pandemic with all the limitations in such a great manner. I indeed appreciate your effort, ma'am. Telling my feedback in the sense, initially I was very hesitant to attend the meeting because suddenly attending for a 5-day program at a stretch was really making me lazy. But I thought of attending the first session and then I thought I'll see. But the first session by Dr. Girija Vallavan sir made me sit for all the 16 sessions till now. And when I joined for each meeting, the presentations were well researched, and it really helped me move forward in my project, as well as upgrading my knowledge in the recent trends of photonics. And I thank you, and I thank all the resource persons for putting extra effort during these difficult times, and I truly appreciate them. I'm indeed looking forward for the next FTP program, and hopefully not in an online mode, because it was a great loss for students like me for not meeting the speakers in person. So yeah, it was a great event. Thank you, ma'am. Thank you very much.
Thank you, Anita. Next, I welcome Archana TC for the feedback.
Hello, everyone. Can you hear me?
Archana, you are audible.
Okay. Actually, first of all, congratulations to all the organizers, coordinators, everyone, and the presenters of this FDP. They've done a very wonderful job. And actually, conducting these sessions, that too with the constraints of internet issues and everything, is very difficult. So they've done a really good job. And the sessions, the topics of the sessions were very relevant, especially starting from the story of light, and then going to biophotonics, sensors, and then optical switches, and even we have discussed the integration, photonic integrated circuits, and the talks on microwave photonics. Everything was really good, and that it is very good that they are providing the recorded sessions, because in my case even I couldn't attend a few of the sessions due to some other classes. So it is very good that they have shared this recordings. It was really useful, and in fact I saw one of the recordings, and it was based on the story of light by Girija Vallavan sir, and it was really interesting because we got to know that even before like a long time back, that is in the 8th century, if they should calculate a value of the speed of light almost similar, that Vateshwar in the 8th century, the what he said about the speed of light and the ancient things, all those were really very interesting. And all the presenters, uh, they've done a very good job of presenting not just the topic but also discussing the practical applications and what all we should see when we are designing a system, or we are considering a certain laser or something for a particular application. and the examples also were very good. When many examples were relatable, and it was a wonderful session, except for the usual problems which occur in an online session like this, that is the internet issues and things. There was no other problem that was found. So once again, thank you so much for this wonderful session.
Thank you, Archana, for the feedback. Is there anyone willing to give the feedback? Can come forward. We request the participants outside from Kerala also can come forward and give the review of this webinar session.
Participants, come forward and give some feedback. Dr. Rampada.
Hello. Hello, ma'am.
Yes, sir, you are audible.
Yes, ma'am. Myself, Dr. CP Singh, at the register number 46. Am I audible, ma'am? Am I audible?
Yes, sir.
I'm from UP, Uttar Pradesh, CCS University, Meerut, Uttar Pradesh. And this is my first specialized FDP ATAL program. And first of all, I would like to congratulate and best wishes for all of the organizers. They organized the FDP program in such a fabulous way. And the other we have the talks from such a learned scientist personalities, emeritus professor and other professors and associate professors in a very specialized way. And I learn a lot of from the FDP. So thank you very much. Thank you. Thank you, ma'am. Am I audible, ma'am? Am I audible?
Yeah, yes, sir. Yes, sir. Yes, sir. Thanks.
Thank you. Thank you very much, ma'am, and all of the organizers of the FDP ATAL.
Okay, sir.
Next, let me invite Indumati for giving the feedback. Ma'am, you can unmute and talk. I think due to some technical issue, Indumati is not able to give the feedback. Is there anyone else?
Hello, madam. Are you
Yes, sir.
able to listen me?
Yes.
Sir, good evening, sir.
Good evening. This is Mukesh Kumar from GGSIP University, Delhi.
Hello.
Hello. Are you audible?
Hello, ma'am.
Yes, yes, yes.
I am
Audible.
Indumati, ma'am. Am I audible?
Hello, ma'am. Are you audible?
Hello.
Okay, okay. Both are audible. Both are audible.
Ma'am, can
Indumati.
I give feedback, ma'am?
Yes, 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 yes. Just give your feedback.
Thank you, ma'am. Thank you, ma'am. Good evening to all. I am Indumati, Assistant Professor in Physics Department, Knowledge Institute of Technology, Salem District, Tamil Nadu. I am very happy to deliver my feedback in this auspicious occasion. This FDP is very useful for improving our knowledge. All the speakers in all session delivered the presentation very nicely and very interesting. Thank you for all the resource persons for such wonderful session. I am thankful to the organizer for conducting such kind of FDP in this pandemic situation. Thanks for this opportunity given. Thank you all. Thank you,
Thank
ma'am.
you,
Thank you,
ma'am.
sir.
Now let me invite Mukesh Kumar for the feedback session. Sorry for the interruption, sir.
Okay. This is Mukesh Kumar from GGSIP University, Delhi. First of all, I would like thanking organizer, and content of the FDP was very good, superb. I hope organizers would hold another FDP sooner in the same area, because the photonics would be the area of the 21st century, and it will, and the electronics would be completely replaced by the photonics. So there is a lot of scope in the photonics area, research and development. So once again, thank you very much for organizing such a beautiful FDP. Thank you, madam. Thank you very much.
You're welcome, sir. Thank you for the feedback. Is there
Okay.
anyone else for the feedback?
Dear participants, we expect more response from participants. Yeah, we need your suggestions and corrections. Then. Thank you. Okay, then only we can correct it when we organize another FTP. Just give your feedback. Amrita madam is there? Dr. Amrita madam? She was an active participant.
Is there anyone else for giving the feedback? You can come forward.
Suggestion മതിയോ? ഇത്ര മതിയോ? ഇത്ര വരെയൊക്കെ ഉള്ളോ? വരണ്ട
I think there are no more feedback from the participant side. Thank you all for giving your feedbacks. Now, let me invite the FTP organizer, Dr. Laila D, for giving the vote of thanks.
A very good afternoon to all. The 5 days FTP organized by Model Engineering College has come to an end today. In this moment, I would like to thank the director ICT Adel Academic itself for providing us with a chance to organize and conduct their UP in online mode even during this COVID-19 pandemic situation. I extend my thanks to Dr. Vinay Thomas, Principal Model Engineering College, for the support and cooperation given to organize this event. We have been fortunate to have the eminent experts from various academic institutions, industries, and research centers to share their knowledge and experience with us. I am very thankful to all the speakers for sharing their graceful words with us. Special thanks to Sri Sajisham and Manoj Kumar P, assistant coordinators, my colleagues, for their immense support and cooperation to organize this event. Last but not least, I would like to thank our PG students for the technical and overall support and help given to me. And Mr. Swad, Ravina, and Amrita, and Anisiba, they were with me during these 5 days in our lab, our college. All participants were very enthusiastic. The responses received were huge. I hope you will have benefited from the FTP. Thank you all for the participants for the support given throughout the section. I would like to thank all once again for making this event a grand success. Hoping all are healthy and safe during this pandemic situation. Also wishes a very happy Navaratri 2020. I hope you have the best puja and celebrations in life this year. Thank you all. Once again, thank you all.
Thank you, ma'am, for the vote of thanks. Thank you all the participants for the support and coordination throughout the faculty development program. Even in this pandemic situation, support and participation from each of you made this program a grand success. May the Almighty God help us to overcome this pandemic situation and brings everything back to normal. Once again, thanking you all and stay safe. So that's the end of the webinar program. Thank you all.
Thank you, ma'am. Thank you.